Welcome to Module 1 of MEEN 363 Dynamics and Vibrations. Today we will be discussing single degree of freedom vibrations. By the end of this module, you should be able to do the following. You should be able to define the basic terms used to describe vibration systems, and you should be able to identify damped and undamped systems from differential equations, graphs, and videos. Vibrations have two main parameters, amplitude and frequency. Frequency is how often a system completes a full cycle. It can have the units of radians per second or hertz. The SI unit for frequency is radians per second. Always convert frequencies to radians per second when being used in equations. To convert from radians per second to hertz, use the following equation. Omega is equal to 2 pi f, where omega is in radians per second and f is in hertz. Amplitude is the maximum value a system can have. It is usually on the y-axis of a graph. As you can see from the image, the amplitude is the distance from 0 to the very top of the wave. We have a generalized single degree of freedom equation. It is described by x double dot of t plus 2 zeta omega n x dot of t plus omega n squared x of t is equal to f of t. So I'll go ahead and define what each parameter is. So x of t is the displacement of the system in meters, x dot of t is the velocity of the system in meters per second, and x double dot of t is the acceleration of the system in meters per second squared. We also have zeta, which is the damping ratio, which is unitless. We'll go over the damping ratio in a bit. Also, we have omega n, which is the natural frequency in radians per second. We'll also discuss what the natural frequency is. And f of t is the external force on the system, which is in newtons. A system that exhibits damping is a system where amplitude decreases with time. The higher the damping ratio, the less time it takes to reach an amplitude of 0. As you can see from this graph, we have three different systems with three different damping ratios. The white graph has a damping ratio of 0.005, the red one has a damping ratio of 0.05, and the yellow one has a damping ratio of 0.1. As you can see, the higher the damping ratio, the less time it takes to go to 0. The natural frequency is the frequency at which a system vibrates at naturally. Every system has a natural frequency. We will start our discussion with unforced vibration. Unforced vibration is when a system has no external force. So in terms of the differential equation, there is no particular solution. And also with respect to the generalized equation, f of t is equal to 0, as you can see on the right-hand side of the equation. Two subcategories that we'll be looking at are the undamped and damped vibrations. Undamped vibrations do not exist in real life, however they must be studied as they are the most basic system. In undamped vibrations there is no damping, so zeta is equal to 0 in the system. And you can see that the generalized equation simplifies to x double dot of t plus omega n squared x of t is equal to 0. And we can also find the mathematical solution of this differential equation, which is x of t is equal to c1 sine omega n t plus c2 cosine omega n of t, where c1 and c2 are constants that we can find using the boundary conditions. A system that is undamped exhibits no reduction in amplitude. So we'll be using this video in order to show what an undamped vibration looks like. So you can see this is vibrating with constant amplitude, and there is no decrease in amplitude with respect to time. This means that it is an undamped vibration. Damped vibrations are vibrations where amplitude decreases with time. So damping is the lessening of amplitudes with respect to time. Damped vibrations are described by the following differential equation. So you can see that since zeta is not equal to 0, we have that middle term, 2 zeta omega n x dot of t. We also have the mathematical solution of the differential equation. X of t is equal to exponent negative zeta omega n t times c1 sine omega dt plus c2 cosine omega dt. The exponent negative zeta omega n t term means that the amplitude is decreasing exponentially with time. So we will see that in the next slide. So here you can see that as we're going to let go of the mass, we can see how the amplitude is actually decreasing with time. Here, this means that there is damping and it is considered damped vibration. There are 3 different types of damped vibrations. There's underdamped, where zeta is less than 1, critically damped, where zeta is equal to 1, and overdamped, where zeta is greater than 1. This course we will study most of the underdamped vibrations, but it is important to know the 3 types of damped vibrations. You can see from this graph what is the effective zeta and what does it mean. You can see that when zeta is equal to 0, there is no decrease in amplitude. As zeta increases, there is a decrease in amplitude with respect to time. You can see that for zeta is equal to 0.1, 0.2, 0.4, 0.7. Zeta is equal to 1 is critically damped vibration. You can see it goes very quickly to y of t is equal to 1. And for zeta is equal to 2, this is overdamped. You can see that it takes time to get to its steady state value. So this is the end of our lesson, and I hope you enjoyed it. These are some questions that you should be able to answer by the end of the lesson. If you're unable to answer them, go back through the slides and review the material and try to answer these questions as you go along the material once again. Of course, these are the sources for some of the pictures that I've used in this module.